In this unit, we're going to talk about exponential functions. That is a function that we just kind of glanced over when we were talking about transformations, but now we really want to focus in on what the exponential function looks like. To start today, we're going to talk about exponential growth. So imagine that you have bacteria in a petri dish, and it grows so that it triples in number every day. Now, currently, the bacteria has a population of 100. Determine the population after each of the first 4 days. So there's some important stuff to realize when we're looking at this type of a problem. The first thing is that it's triple, so it's tripling, which means that every day, after every day, we're going to have to multiply it by 3 because it's going to be tripling. The other thing to take note of is where it begins at. So it starts with a population of 100. So at day 0, that would be our starting day, we have 100 bacteria. Now, after a day has passed, so 1 full day has passed, we would then be up to 300 bacteria because I take my 100 and I triple it, so I multiply it by 3, which brings me to 300. And then after 2 days, so another day's gone by, this 300 has now tripled, and so I'm at 900. And then after 3 days, so another day goes by, this 900 triples again, so now I'm at 2,700. And then after the 4th day, another day goes by, and we're multiplying this by 3 again, and I get 8,100. And as you can see, the growth rate with something that we're multiplying by 3 each time increases very fast. So we started with 100, and after only 4 days, we're up to 8,100, which is huge. Okay. So calculate the finite ratios. So this is a little different from finite differences. Finite differences, we would start at the bottom and then subtract our way back up. With exponential, instead of subtracting, we're actually going to divide. So we're going to figure out the ratio of this. So I'm still going to start at the bottom, 8,100, and then I'm going to divide it by the number above. And notice when I have 8,100 divided by 2,700, I get 3. And then let's do this again. 2,700 divided by the number above it, and I get 3. 900 divided by the number above it, and I get 3. And then 300 divided by the number above it, and I get 3. And it makes sense for us to get this number 3 because the number that should come up should be the exact same number. So this should end up being the exact same number as what the descriptor was. And it was telling us it was tripling, so we should see that that ratio is a 3. Okay, so same problem. Determine an equation for the growth of bacteria. So we got to think about how we can write this as an equation. So let's say we're going to let A equal the amount of bacteria. And we can say that M is our starting amount. So how much bacteria did we have to begin with? B is going to be our growth rate. Okay, and X will represent time. Okay, so how much time has gone by? So we can use all this information in this formula. A equals M times B to the exponent X. And that can represent our exponential growth. So in this case, our amount of bacteria is going to be equal to our starting point, which was 100, times by our growth rate, which is tripling, so times 3 to the exponent x, and this is time, and in what we're talking about here, it's in days. Okay, so then this represents our equation. Now it says use your equation to predict the population after 2 weeks. So after 2 weeks, because this is time in days, we're going to have to put that into days, which is 14 days. All right, so amount of bacteria is equal to 100 times 3 to the x. And in this case, I know that x is going to be 14. Now, when you work this out in your calculator, you have to remember bed mass. So bed mass, of course, tells us our order of operations. So brackets exponents, so that means you need to figure this part out first and then multiply it by 100. So very important that you do this, the order of operations correctly. You are not going to take 3 times 100, 300, and put it to the exponent 14. That would give you a really, really huge number. So we're going to go 3 to the exponent 14, and I'm going to hit equals in my calculator, and then I'm going to times that by 100. And when I do, I get 4, 7, 8, 2, 9, 6, 9, 0, 0. So let me just put in some commas here to help me. So I get 478,296,900 bacteria. Holy smokes, that's a lot of bacteria after 2 weeks. Okay, so the big one on this is just to be sure that you work out the 3 to the 14 first on your calculator, and then take your answer and multiply it by 100. This is also very important. Of course, this will be our equation that will help us come up with equations, exponential equations, depending on the information given. So let's take a look at another example. So here we have different situations. We just want to be able to write the equation. So here's my first one. A bacteria culture has 10 cells. It doubles every day. So here's our 2 pieces of information. This is our starting point. This is how much it has to begin with. And here's the other keyword, it doubles. So doubles means times 2. That is my growth rate. So I'm going to call that my GR, my growth rate. So we know that the amount of bacteria is M times B to the X. And in this case, M is 10. B is 2, that's my growth rate, to the power x, which we don't know how much time has gone by. All right, let's try another one. Okay, so an antique is currently valued at $200. It increases in price by 20% each year. Okay, so these ones that talk about increasing rate or decreasing rate, we have to think about it a little bit. If it's increasing in rate, then it's increasing by 20%, then we go 1 plus that 20%. The 1 means it's keeping its original value, and then we're going to add another 20% of that value onto it. So of course we can't add these 2 together because 1's a number and 1 is a percent. So I'm going to change that percent to a decimal, which is 0.20. And so this becomes 1.20 becomes my growth rate. This 200 is my M value. So that's where we're starting at. So A, whoops, sorry about that. A equals my original, which is 200, times by my growth rate. Whoops, sorry about that. Let me just change that. 1.20 to the exponent x. Okay, so that's how you write it. If you're talking about something that's increasing in price, you go 1 plus the percentage. If you were talking about something decreasing in price, you go 1 minus the percentage. And we'll see that a little bit later on. Okay, let's pull out C. Oh, here we go. A new car is valued at $15,000. And its value depreciates. So depreciates, of course, means it goes down at a rate of 24% per year. So if it starts at 1 means it's staying the same. It's going to depreciate by 24%, which is the same as 1 minus 0.24, which equals 0.76. So this is the growth rate. It's actually it's a decay rate because it's going down in value, which makes sense because it's depreciation. This is where it started at, so that's my M value. So A equals 15,000 times my growth rate, which is 0.76 to the exponent X. Okay, so if it's increasing, we add. If it's decreasing or depreciating, then we subtract. All right, last one. Okay, so a bacteria culture of 40 cells, and it triples in size every 5 days. Ooh, okay. So let's talk about this a little bit. So here's where we're starting at. 40 cells, there's my M, and it triples in size, so we're multiplying by 3, so that's my growth rate. But every 5 days, so we're going to have to take a look at that in terms of time, okay? And I'll show you what we can do with that in just a moment. So let's begin. The amount is equal to 40 cells times by it tripling. Now, normally we would just put this to an X, but if I put in an X, then what that represents is each day, right? And it doesn't triple each day. It only triples after 5 days have passed. So if we leave this as an X, then the actual answer we're not going to get is only one that doesn't represent it properly. So instead, I'm going to divide this by 5. And that then can represent over 5 days, because if I put in a 1 here for 1 day, that 1 over 5 becomes 0.2, which makes sense because we're only at, 0.2 of the 5 days. And if I put in 5 days, 5 over 5, which equals out to 1, so there would only be 1 growth rate, which makes sense if it's happening only every 5 days. So just be very careful. If you get that it's growing, but only after so much time, then we have to include that into our equation. Okay, so a few notes on this. So you might want to pause here to take these notes. We have our independent variable increases by a constant amount. The dependent increases by a common factor. So that's our multiplying it by 2 if it's doubling, multiplying it by 3. It's whatever the growth rate is, okay? So it's increased by a common factor. I'm going to just put here growth rate. The graph increases at an increasing rate. The finite differences has a repeating pattern. It's the ratio, okay? So we use a ratio, and it's nice because that ratio that we figure out is actually what our growth rate is. And the graph of an exponential growth can be modeled by A equals M times B to the X, where M is the initial value and B is your growth factor. So make sure you have these written down. It's good information. And then, of course, here is some homework that you can certainly practice on. If you have any questions, let me know.